In this video, we'll talk about the definition of sine and cosine in terms of the unit circle. First of all, we should define the unit circle. The unit circle is the circle with radius 1 centered at the origin of the xy plane. So the equation of the unit circle is x squared plus y squared equals 1. In order to define the sine and cosine functions, we'll make use of this unit circle. So first draw the unit circle, and then draw a central angle in the unit circle in standard position, so that the initial side is along the positive x-axis, and the terminal side forms an angle of measure theta. The point where the terminal side of the angle intersects the unit circle has coordinates where x is cosine theta and y is equal to sine of theta. This is how we define cosine of theta and sine of theta. They're defined to be the coordinates of the point formed in this way, where the initial side is along the positive x-axis and the terminal side forms an angle of measure theta. Let's relate sine and cosine to a right triangle. The coordinates of the point cosine theta and sine theta give the height and base of a right triangle having, well, I say radius 1 because it's the radius of the circle, but really having hypotenuse of length 1 and having an angle theta. We can use this relationship to compute values of cosine of theta and sine of theta for certain important values of theta. For example, where the circle intersects the positive x-axis, since this equation, the equation of the circle, is x squared plus y squared equals 1, we know that the radius in particular is r equals 1. So that means that this length is 1. So the x-coordinate of the point where the circle intersects the positive x-axis is going to have value 1, and the y-coordinate is going to be 0 because it's intersecting the x-axis. This tells us that cosine of 0 is equal to 1, and sine of 0 is equal to 0. Because if we're looking along the positive x-axis, that means theta is equal to 0 in this case. What about where it intersects the positive y-axis? Here. This is now an angle of 90 degrees, or pi over 2 radians. So if we go all this way, this is an angle of pi over 2. The coordinates here are 0, 1, again because this is a circle of radius 1. So that tells us that cosine of pi over 2 is equal to 0, and sine of pi over 2 is equal to 1. If we continue around the circle and look at where it intersects the negative x-axis, in this case we're looking at an angle of 180 degrees, or pi radians. And the coordinates here are -1, 0. So that tells us that cosine of pi is -1, and sine of pi is 0. If we take another quarter rotation, that puts us here. This is now 3 pi over 2. And the coordinates here are 0, -1. So cosine of 3 pi over 2 is equal to 0, and sine of 3 pi over 2 is equal to -1. So these are some of the important values of sine and cosine. Another important angle is theta equals pi over 4, which is 45 degrees. So here's a picture of the first quadrant. Here's the unit circle, or at least the amount of the unit circle that you can see in the first quadrant. Here we've drawn an angle of measure pi over 4, or 45 degrees. The coordinates of the point where we intersect the circle has x value square root of 2 over 2 and y value square root of 2 over 2. That's true because this is now an isosceles right triangle that you see here. This angle measures 90 degrees, or pi over 2. Pi over 4, that's 45 degrees. Let's write this in degrees. So that's 90 degrees. This is 45 degrees. So since the angles of a triangle have to add up to 180 degrees, that means that this is 45 degrees as well. So what that tells us is that this is an isosceles right triangle with hypotenuse length 1. So this length is the same as this length. The base is the same as the height. So if we call that value a, it's the same for the base and the height. So a squared plus a squared is equal to 1 squared, which is just 1. So that means 2a squared is equal to 1. So a squared is 1/2, and a is equal to, well, plus or minus the square root of 1 over 2. We're looking at positive lengths here because they're the side lengths of this triangle. So we just take the positive square root. So a is equal to the positive square root of 1/2. Now if we rationalize the denominator, so a is 1 over the square root of 2, if we rationalize the denominator, we end up with the square root of 2 over 2. And that's where these values come from. Remember, the x-coordinate is how far off to the right we are, which is now, we know, square root of 2 over 2. And the y-coordinate is how high above the x-axis we are, and that's also square root of 2 over 2. So cosine of pi over 4 is square root of 2, and sine of pi over 4 is also square root of 2 over 2. Our next important angle is pi over 6. Pi over 6 is 30 degrees, so this is a 30-degree angle. We know that this is a right triangle, so again this is 90 degrees, and that means that this remaining angle is 60 degrees. So we have a 30-60 degree right triangle. This information will allow us to determine what the coordinates are of this point. In fact, we can show that the x-coordinate is the square root of 3 over 2, and the y-coordinate is 1/2. So that tells us that since cosine of pi over 6 is the x-coordinate, cosine of pi over 6 is the square root of 3 over 2. And since sine will give us the y-coordinate, sine of pi over 6 is 1/2. This length right here, that's sine of theta. In this case, theta is equal to pi over 6. Now, how do we determine that these are the coordinates? Well, remember what these represent. The x-coordinate tells us how far we are. So how far we are to the right. And the y-coordinate tells us how high above the x-axis we are. So that's y. We know that x squared plus y squared is equal to 1 squared, or just 1. So we're going to use this fact to determine these values. Well, that and a little something else. Because this is a 30-60 degree triangle, what I'm going to do is I'm going to reflect this entire picture through the x-axis to create a slightly larger triangle, a triangle of double the size. So let's attempt to do that. So let's just draw a little bit of this circle right here. Well, that's a terrible circle, but let's just try a little bit harder. So something like that. That's just a little bit more of it. And I'm going to double this angle, so it looks something like this. Something like that. And then we just draw like this. So that's not quite straight. Something like that. There we go. So this angle is 30 degrees. I know it's 30 degrees because I'm just reflecting this whole picture through the x-axis, so I'm doubling the angle. Well, that tells me that I have a 30-degree angle and a 30-degree angle, so altogether this is going to give me 60 degrees. This angle down here is also 60 degrees because it's the reflection of this angle up on the top through the x-axis, so it's also 60 degrees. Well, that tells me that I have an equilateral triangle. All of the angles are equal, and that means all of the sides are equal as well. So all of the sides have length 1. This one here also has length 1. So this thing is length 1. This length y is the same as that length y. That length is also y. which means it's half of the total, which is 1. So the total is 1, so half of it should be 1/2. So that tells us that y is 1/2. So that's where that 1/2 comes from. What about the base of this triangle, which is the length x? Well, now we use this equation, or we use the Pythagorean theorem. X squared plus y squared is equal to 1. But we know that y is equal to 1/2. So x squared plus 1/2 squared is equal to 1. X squared plus 1/4 equals 1, so x squared is equal to 1 minus 1/4, which is 3/4. Now we compute the square root of that. So x is equal to plus or minus the square root of 3/4. Well, x is a length, so it's going to be positive, so we pick the positive square root. So x is equal to the square root of 3 over 4, which is the square root of 3 over 2. So the x-coordinate is the square root of 3 over 2. So that's how we know that cosine of pi over 6 is square root of 3 over 2, and sine of pi over 6 is 1/2. So sine is 1/2, and cosine is square root of 3 over 2. Our next important angle is theta equals pi over 3. Pi over 3, that's 60 degrees. And this is a right triangle, so that means that the remaining angle is 30 degrees. So that tells us already everything that we need to know, because this triangle is the same as the previous triangle. So that means the short side is 1/2, and the long side is square root of 3 over 2. So the short side is 1/2, and the long side is square root of 3 over 2. Because this triangle is the same as the triangle above, just moved around a little bit. But the dimensions are the same, because it's a 30-60 degree triangle where one of the sides, the hypotenuse in fact, is length 1. So that means that the shorter side is 1/2, and the longer side is the square root of 3 over 2. Well, the shorter side, that's how far off we are to the right. That's the x-coordinate. So that tells us that cosine of pi over 3 is 1/2. The longer side, this is sine. This is sine of theta. The y-coordinate, it tells us how high up above the x-axis we are, and it's square root of 3 over 2. So that tells us that sine of pi over 3 is square root of 3 over 2. Here we've summarized our information for the first quadrant. We have the angle here for pi over 6, where we have 30 degrees. Pi over 6 is 30 degrees. The coordinates there is square root of 3 over 2 and 1/2. Pi over 4 is 45 degrees. The coordinates are square root of 2 over 2 and square root of 2 over 2. And pi over 3 is 60 degrees, and the coordinates are 1/2 comma square root of 3 over 2. What we need to remember is that the x-coordinate is cosine of theta, and the y-coordinate is sine of theta. So cosine of theta is x, and sine of theta is y. We also have 0 here. 0 degrees is the same as 360 degrees, so that's also 0 radians, or 2 pi radians. Here we also have pi over 2, which is the same as 90 degrees. So this tells us that cosine of 0 is 1, and cosine of 2 pi is also 1. Sine of 0 is 0, sine of 2 pi is 0. Over here we have that cosine of pi over 2 is the x-coordinate, which is 0, and sine of pi over 2 is 1. So this is a picture that we want to remember, because we'll need to know these angles. The main reason we want to know about those angles is that we can use those angles to help us to compute the sine and cosine of a lot of other angles in the other quadrants. So in order to compute these values for angles not in the first quadrant, we make use of what we call reference angles. So given an angle theta in standard position, the reference angle for theta is the acute angle formed by the terminal side of theta and the x-axis. So if you're in quadrant 1, then the acute angle is theta. So the measure here is theta. So the angle that we're looking at is theta. Now the acute angle made with the x-axis is theta itself. So the reference angle here is theta. Let's call the reference angle, let's give it some name. Let's call it alpha, just to make it easier to write down. So If you're in the first quadrant, then alpha is actually equal to theta. If you're in the second quadrant, that means you're over here. So first of all, what is theta? Theta is the angle from the positive x-axis to the terminal side. So theta is this wide angle here. So that's theta. The smaller angle, that's the acute angle. And this is the reference angle, so this is alpha. So in this case, you can see that alpha plus theta is going to give you 180 degrees, or pi radians. So in this case, alpha is equal to pi minus theta. Notice that this measure, alpha, is the same as the measure of this angle in the first quadrant. What about quadrant 3? Quadrant 3 is here. So again, theta is the measure of the angle from the positive x-axis to the terminal side, so it's this very wide angle here. That's theta. Alpha is this angle. This angle. Alpha is the acute angle formed with the x-axis. There are two angles formed with the terminal side and the x-axis. One of them is this acute angle, which we're calling alpha. The other one is this obtuse angle, which we're not calling anything. We're going to pick the acute angle because that's our reference angle. In this case, alpha is equal to theta minus pi. Because pi is 180 degrees, so the measure of the half rotation is going to not quite get you to theta. So there's a little bit more. So pi gives you a half rotation, but then you continue, there's more rotation here. So that little bit more is equal to alpha. So in other words, theta is bigger than pi, and that difference is alpha, the reference angle. Notice that in this picture that this alpha is the same as the measure of this angle alpha in the first quadrant. That's going to be important for later. In quadrant 4, theta, again, it's the angle from the positive x-axis rotating counterclockwise till you get to the terminal side. So this is our angle theta there. Alpha is the acute angle made with the x-axis. So this is alpha. It's this angle here. The x-axis makes two angles with the terminal side of theta. One is here, this is our obtuse angle, here, and our acute angle is here, which we're calling alpha. Alpha is the measure of that angle. Now in this case, we see that theta is not quite a full rotation. Theta is short of a full rotation by the amount alpha. So that means that alpha is the difference between a full rotation and a rotation by theta. So alpha is equal to 2 pi minus theta in this case. Now once again, notice that alpha is equal to an angle in the first quadrant. These angles alpha are the reference angles. And the reason that they're useful is that alpha is always in the first quadrant because it's an acute angle. So in the first case, alpha is equal to theta. But in the other cases, you can see that alpha is an acute angle which appears in the first quadrant. And the coordinates corresponding to the reference angle will be the same as the coordinates for the actual angle theta, except maybe you'll have a minus sign in front. So in the first quadrant, alpha is equal to theta. So this has coordinates x comma y, where both x and y are positive. If theta is in the second quadrant, which is what you see here, then the reference angle is still in the first quadrant, so it has coordinates x comma y. Theta, on the other hand, will have the same coordinates, but there will be a minus sign in front of the x, minus x comma y. Y is the same because y is telling you how high up above the x-axis you are, and that's the same for both of these points. The x-coordinate is the opposite because alpha's x-coordinate is to the right of the y-axis, But theta's x-coordinate is to the left of the y-axis, but it's by the same amount. So if alpha gives you x-coordinate x, then theta gives you x-coordinate the opposite of x. If you're in quadrant 3, then the reference angle will give you x comma y, where both x and y are positive. And theta will give you coordinates negative x and negative y, because it's in the third quadrant. And both x and y are negative in the third quadrant. In quadrant 4, the reference angle will have coordinates x comma y, and the angle theta will have coordinates x comma negative y. The x is the same because you move to the right of the y-axis by the same amount, but now you're moving below the x-axis, so the y-coordinate is going to be negative. These coordinates, x and y, represent cosine and sine of the angle alpha. So what this tells us is that if we want cosine and sine of the angle theta, we just need to find the values of cosine of alpha and sine of alpha, and that will give us the same values as cosine and sine of theta, although we might have to put a minus sign in front of something depending on which quadrant we're in. Now we've summarized that on this next slide. A reference angle always has angle measure between 0 and pi over 2. Now this is an inclusive, so it might include 0 or pi over 2, which is the same as 0 degrees and 90 degrees. So as I've said already, angles have the same sine and cosine values as the reference angle, except maybe the sine, which is determined by the quadrant. In the first quadrant, everything's positive. In the second quadrant, the x-coordinate is negative, but the y-coordinate is positive. In the third quadrant, they're both negative. And in the fourth quadrant, x is positive, but y is negative. So you can find the values of sine and cosine for the reference angle, which will always give you something where x and y are positive. And then you just determine which one of these is positive and which is negative, and that will give you the value of cosine and sine of theta, and that depends on which quadrant you're in. Let's look at an example. Find the reference angle for theta equals 2 pi over 3 and use it to compute cosine of theta and sine of theta. So the first thing to do is to draw a unit circle. So let's just draw a circle quickly, and let's put in some x-axis and a y-axis like so. All right, now we're interested in theta equals 2 pi over 3, which is about here, something like this. So this is the angle 2 pi over 3. We want to know the coordinates of that point there, where this is the circle x squared plus y squared equals 1. So the radius here is 1. We want to know the coordinates of that point. In order to do that, we're going to look at the reference angle. Now the reference angle is over here. It's this angle. Now this angle, the reference angle, is pi over 3. So we have 1 pi over 3, this one is 2 pi over 3, and 180 degrees is 3 pi over 3, which is pi radians. Let me just move this so it's not overlapping. So this angle here, this angle is 2 pi over 3. 2 pi over 3 like that. Okay, now the reference angle is pi over 3, and we know the value of sine and cosine of pi over 3. We've already computed that. So this is the one where x is 1/2 and y is the square root of 3 over 2. So this is 1/2, and this is the square root of 3 over 2. So that's for the reference angle. So that means that our actual angle theta here has coordinates which are the same numerically but might have a minus sign. This is the second quadrant, so that means we're going to have a negative on the x but a positive on the y, because we're in the negative x direction but the positive y direction. So that means the coordinates are minus 1/2 and positive square root of 3 over 2. And these give you the values of cosine and sine of theta. So cosine of theta, which is 2 pi over 3, is equal to negative 1/2. It's supposed to be a 2. And sine of 2 pi over 3 is equal to the square root of 3 over 2. And those are your answers. We were able to compute this using the reference angle because we knew the values of cosine and sine for the reference angle, and we used those to determine the values of cosine and sine for the angle theta. Let's do another example. Find the reference angle for theta equals 3 pi over 2, and use it to compute cosine of theta and sine of theta. Well, 3 pi over 2, let's draw a unit circle and draw our x and y axes like so. I think that moved just a little bit. Let's put it right there. Okay, so this is x, this is y. Again, this is the unit circle, so it has equation x squared plus y squared equals 1. It's the circle of radius 1, centered at the origin. Theta equals 3 pi over 2 is 3/4 of a rotation. So that puts us here, 3 pi over 2. That puts us right there. Actually, this one is easy because we already know what the coordinates of this point are. The x-coordinate is 0 and the y-coordinate is negative 1. But what is the reference angle here? The reference angle is the acute angle made with the x-axis. Well, in this case, it's not exactly an acute angle, it's a right angle. It's this angle, pi over 2. So that's our alpha in this case. Alpha is equal to pi over 2. So our coordinates for this point are 0, 1. And as you can see, our coordinates for theta are the reflection through the x-axis. So in this case, we have cosine of theta, which is 3 pi over 2, is the x-coordinate, which is 0. And sine of 3 pi over 2 is equal to negative 1. And that's our answer. Notice that the values are the same as for our reference angle, but just with a minus sign in front of the y-coordinate in this case. On our next slide, we have the unit circle together with the coordinates for most of the commonly used angles. For example, we have that 30 degrees is pi over 6, and the coordinates of that point are the square root of 3 over 2 and 1/2. So cosine of 30 degrees is square root of 3 over 2, and sine of 30 degrees is 1/2. Normally in mathematics, we stick to the radian measure, which in this case would be pi over 6. Another common angle, for example, would be 200 degrees, which is 7 pi over 6. And the coordinates here are negative square root of 3 over 2 and negative 1/2. The reference angle for 7 pi over 6 is pi over 6. So these coordinates are the same, but just with minus signs in front of both, because this is in the third quadrant. So these are the most commonly used angles together with their coordinates on the unit circle, which give you the cosine and sine of those angles. We can give some properties of the sine and cosine functions based on the definition. The definition is illustrated here. We have the unit circle, which is, of course, x squared plus y squared equals 1. That's the equation of that circle. And if you have an angle theta, then the coordinates of the point, which is created by the intersection of the terminal side of the angle theta and the unit circle, has coordinates cosine theta and sine of theta. This is how we define cosine theta and sine of theta. So based on this definition, there are certain properties which we can see. For example, Theorem 3. For sine and cosine, the domain for each one of these, the domain is the set of all real numbers, and the range is the set of numbers from -1 to 1, including the endpoints. Why is that? Well, the domain is any value that you can put in for theta, and you can put in any number, any real number for theta. If theta is positive, it represents a rotation in the counterclockwise direction. If theta is negative, it represents a rotation in the clockwise direction. And the larger that theta is, the bigger the rotation is. You might rotate around multiple times, either counterclockwise or clockwise. So that's why the domain is the set of all real numbers. The range is the set of all real numbers between -1 and 1, because if you look at the graph, you can see that these are the largest values you can get for x or y on the unit circle. Let's look at cosine theta. Cosine theta is the x-coordinate. The x-coordinate is how far to the right you go and how far to the left you go. That will give us the range of cosine. So you can see that the smallest possible value of x is right here, where x is -1. And the largest possible value for x is right there, where x is equal to +1. That's 1.0. So you can see that -1 is less than or equal to x is less than or equal to 1. But x is cosine theta. So in other words, -1 is less than or equal to cosine of theta is less than or equal to 1. Notice that you actually can equal 1 or -1. So that's why we have less than or equal here. So that tells us that the range is the set of all real numbers between -1 and 1, including the endpoints. The same is true for sine of theta. Sine of theta is given by y. The largest that y can be is right here. Y can be 1. And the smallest is right here, where y is -1. So -1 is less than or equal to y is less than or equal to 1. So sine of theta is between -1 and +1. And again, we can include the endpoints because at this peak right here, y is actually equal to 1 when x is 0. And down here, y is actually equal to -1, again, where x is 0. So we have that sine is always between -1 and 1, but it could be equal to -1 or 1. So again, the range is the set of all real numbers between -1 and 1, including the endpoints. Here's another property. Theorem 4. If a circle has radius r, then any point P on the circle will have coordinates r cosine of theta and r sine of theta, where theta is the angle that has terminal side that intersects the circle at the point P. So this point right here is what we were calling the point P. And it has x-coordinate r times cosine theta, x equals r cosine of theta, and y is equal to r sine of theta, where the radius of this circle is r. Now, in this drawing, the smaller circle is the circle of radius 1, so we're imagining that the unit circle is smaller. So r is then bigger than 1 in this picture. It would also be true if r was smaller. Then you would just have a circle inside the unit circle. So there would just be some circle there. We can show that the coordinates of the point are what you see here. So x equals r cosine theta and y equals r sine of theta using the properties of similar triangles. So we've reproduced here just the first quadrant of the previous picture. So we have a circle of radius r, or at least this is an arc of the circle which appears in the first quadrant. So this is radius r, so this length is r, this length is r. Here we have the unit circle, or at least the arc that appears in the first quadrant. So that's length 1, that's length 1. The coordinates here are x comma y. Now what about the coordinates here? So this is the unit circle, this angle is theta, so we know what the coordinates of this point are. This point has coordinates cosine of theta and sine of theta. But these coordinates represent dimensions of this smaller triangle right here. So this smaller triangle here has dimensions given by the coordinates of this point. So the x-coordinate tells you how far out to the right you go. So the smaller side of this triangle has length cosine of theta. So this length right here is cosine of theta. And the y-coordinate tells you how high up you are. So that means that this length here is sine of theta. Now notice that this larger triangle is similar to the smaller one. So that means that their ratios the ratios of common sides are equal. Now, the hypotenuse of the big triangle is r, because that's the radius of the circle, and the hypotenuse of the smaller one is 1. So the smaller hypotenuse here has length 1. So if we want to determine, say, the value of x, and the value of x is the length of the smaller side of this triangle. So what we can say is that the value of the large base to the value of the small base is in the same proportion as the large hypotenuse, which is r, to the smaller hypotenuse, which is 1. So now if we cross multiply, we get that x is equal to r times cosine of theta. And we can do the same thing to determine the value of y. The value of y is the height of this larger triangle. So we can look at the ratio of the corresponding sides. So y to sine of theta is equal to r to 1. So the altitude or the height of the big triangle compared to the height of the small triangle is equal or in the same ratio as the hypotenuse of the large triangle to the hypotenuse of the small triangle. So again, we cross multiply to get that y is equal to r times sine of theta. And that's how we determine that the x-coordinate of this point is r times cosine theta and the y-coordinate is r times sine of theta. Let's look at an example. Find the coordinates of the point on the circle with radius 8 having angle theta equals 4 pi over 3. So the way that we start these problems is we just look at the unit circle. So let's draw a circle, and let's say that this is the unit circle. So this is the unit circle, x squared plus y squared equals 1. Now the circle we're actually interested in has radius 8, but we're going to start with radius 1. And then whatever your answer is, you just multiply it by 8. So here the angle is theta equals 4 pi over 3. So 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi, well that's a little off. 4 pi, oh, that's a little off too. Let's try that one more time. 4 pi over 3 is right about here. So this is the angle 4 pi over 3. So the coordinates here, well, what are those? Well, it helps to look at the reference angle. Now, the reference angle is this angle right here, which is 1 pi over 3. And we know what the coordinates are for that. That's the one that has x-coordinate 1/2 and y-coordinate square root of 3 over 2. If you were ever confused between pi over 3 and pi over 6, pi over 6 is further down. So that means that the y value is smaller and the x value is bigger. So if you're looking at the angle pi over 6, you're dividing by a bigger number than 3, so it's further down. So that gives you a smaller y value, but a larger x value. So that's square root of 3 over 2 and 1/2. But we're not looking at pi over 6 right now. We're looking at pi over 3, which has x-coordinate 1/2 and y-coordinate the square root of 3 over 2. Now our actual angle is 4 pi over 3. That's in the third quadrant. So that means we have the same coordinates except minus signs in front of both. So it's going to be minus 1/2 and minus square root of 3 over 2. So that is the value of, or those are the coordinates on the unit circle. So on the circle with radius 8, you just multiply by 8. So the x-coordinate is going to be equal to 8 times minus 1/2, which is negative 4. And the y-coordinate is going to be 8 times negative square root of 3 over 2, which is negative 4 square root of 3. So the coordinates on the big circle with radius 8 are negative 4, comma, negative 4 square roots of 3. This brings us to the last property we want to discuss in this video, which is the Pythagorean identity. So for any angle theta, cosine theta squared plus sine of theta squared is equal to 1. Now that's simply true because the equation of the unit circle is x squared plus y squared is equal to 1. And x is equal to cosine of theta, and y is equal to sine of theta. So if you just plug in cosine of theta in for x and sine of theta in for y, you have the Pythagorean identity. Cosine of theta squared plus sine of theta squared is equal to 1. Notice that here we're actually squaring all of cosine, and we're squaring all of sine, like so. So cosine theta quantity squared plus sine of theta quantity squared is equal to 1. Now this is a very useful identity because it means that if you know the value of sine or cosine, then you can figure out the value of the other one. Up to a sine, you'll need to at least know what quadrant you're in. Let's look at an example. If sine of theta is equal to 3/5 and theta is in the first quadrant, what is cosine of theta? Well, the Pythagorean identity tells us that cosine of theta quantity squared plus sine of theta quantity squared is equal to 1. But we know what sine of theta is. Sine of theta is 3/5. So we just plug in 3/5 there for sine of theta. Cosine of theta is the thing that we're looking for. So we have that cosine of theta quantity squared plus 3/5 squared is equal to 1. So cosine of theta quantity squared plus 9 over 25 is equal to 1. That means that cosine of theta quantity squared is equal to 1 minus 9 over 25, which is 25 over 25 minus 9 over 25, which is equal to 16 over 25. So that tells us that cosine of theta is equal to plus or minus the square root of 16 over 25, which is plus or minus 4 over 5. Now it's the plus or minus that we don't know yet. That's determined by which quadrant you're in. If you're in the first quadrant, then that means x is positive. So that means cosine is positive. So we pick the positive square root. So cosine of this angle theta is positive 4 over 5. Notice that at no point did we determine the value of theta. We don't know what angle theta is, but we do know that if sine of theta is 3/5 and theta is in the first quadrant, then cosine of theta is 4 over 5. Now our next example asks us the same question. If sine of theta is 3 over 5, then what is cosine of theta? But now we're in the second quadrant. So what does that mean? Well, we know the same thing that we knew before. We know that cosine of theta squared plus sine of theta squared, which is 3/5 squared, is equal to 1. That's the same equation as before. So once again, we still know that cosine of theta squared is equal to 1 minus 9 over 25, which is equal to 16 over 25. So cosine of theta is equal to plus or minus the square root of 16 over 25, which is plus or minus 4 over 5. This is the same as before. But now we're in the second quadrant. That means that x is negative now, and x is the cosine of theta. So we choose the negative square root. So in this case, if sine of theta is 3/5 and theta is in the second quadrant, then cosine of theta is equal to negative 4 over 5. So it's the same as before, except now that we're in the second quadrant, the x-coordinate must be negative. Notice that if you're in the first quadrant or the second quadrant, then y has to be positive. So if we draw our xy axes here, this is quadrant 1, this is quadrant 2. So in either of these quadrants, y is positive. So the y value, which is sine of theta, has to be positive. So if we knew that y was equal to negative 3/5, or we knew that sine of theta was negative 3/5, then we'd have to be down here in either the third or the fourth quadrants. In this case, we knew that we were in the second quadrant, and that makes sense because we know that y is positive. In the previous example, we were in the first quadrant, and again, y is positive there. Let's do another example. So now we're in the third quadrant. So in our picture that we had on the previous slide, we saw that the third quadrant was over here. So in this case, you're going to have negative values for both x and y. So what do we know? We're in the third quadrant. Cosine of theta is equal to negative 2/3. Well, this is the x value. So we know that x is equal to negative 2/3. And we know that x squared plus y squared is equal to 1. So negative 2/3 quantity squared plus y squared is equal to 1. So if you square a negative number, you're still going to get a positive number. So this will be 4/9 plus y squared equals 1. So y squared is 1 minus 4/9, which is 9/9 minus 4/9, which is 5/9. So y squared is 5/9, so y is plus or minus the square root of 5/9, which is plus or minus the square root of 5/3. We're in the third quadrant. That means y is negative, so we choose the negative square root. So y is negative square root of 5/3. What we're looking for is sine of theta, but that's y. So sine of theta is negative square root of 5/3. And that's your answer. Once again, we don't actually know the value of theta, but we don't need to know the value of theta. We're not asked to find the value of theta. We're asked to find the value of sine of theta, and that we were able to do just using the Pythagorean identity. But we also need to know what quadrant we're in. The quadrant that you're in will determine the sign, whether it's positive or negative, when you take the square root.